Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever wondered how crystals get their mesmerizing colors? Each crystal, with its unique hue and sparkle, holds a world of fascinating science within its structure. At the heart of this science is the crystal field theory. This theory, as intriguing as the crystals themselves, explains how the interaction between light and the atoms in a crystal leads to the creation of the captivating colors we see. Imagine a dance, a ballet of sorts, where light is the music and atoms are the dancers. When light hits a crystal, the atoms in the crystal absorb some of this light energy, causing the electrons in the atom to get excited and jump to a higher energy level. But these electrons can't stay in this excited state forever. Soon enough, they fall back to their original energy level, releasing the absorbed energy as light. The color of this light depends on the amount of energy absorbed and released, and this is what gives crystals their various colors. But there's more to the crystal field theory than just the colors. This theory provides crucial insights into the behavior of minerals and their properties. You see, the way atoms in a crystal absorb and emit light energy is influenced by the structure of the crystal and the type of atoms it contains. This means that by studying how a crystal interacts with light, we can learn a lot about its internal structure and the properties of the minerals it's made of. In other words, the crystal field theory acts like a bridge, connecting the world of optics with the world of mineralogy and allowing us to understand the complex relationship between light, atoms, and minerals. So, the next time you marvel at the color of a crystal, remember that there's a whole world of science behind that beauty. So the colors we see in crystals are not just for beauty, they tell us a lot about their internal structure and properties. The intriguing world of crystals is a testament to the captivating ways in which science manifests itself in nature. Before we dive deep, let's understand the basics of crystal field theory. Crystal field theory is a model that describes the electronic structure of transition metal compounds, all of which can be considered coordination complexes. Now, what does this mean? Let's break it down. A crystal field is essentially an electric field generated by a crystal lattice. This electric field influences the behavior of the electrons in the atoms of the crystal. Now, let's talk about energy levels. In an atom, electrons reside in specific energy levels. Picture it like a multi-story building where each floor represents a different energy level. Electrons, like residents of the building, can move from one level to another, but to do so they need energy. This is where light comes into play. When light, a form of energy, interacts with an atom, it can cause electrons to move to a higher energy level. But as we know, what goes up must come down. So after a while, these excited electrons return to their original energy level, releasing the absorbed energy as light. This light is what we perceive as the color of the crystal. In a nutshell, crystal field theory is a scientific model that helps us understand how the structure of a crystal influences the behavior of its electrons, and subsequently its interaction with light. With these basics, we are now ready to delve deeper into the crystal field theory. Now, let's delve deeper into the fascinating world of crystal field theory. Crystal field theory, at its core, is the study of energy states or levels of a central metal ion in a crystal structure. Picture it like a grand ballroom dance where the central metal ion is the star dancer, while the surrounding ions are the ensemble, all playing their part in a beautiful and complex performance. The ensemble ions create a so-called electric field, which directly impacts our star dancer, the central metal ion. This interaction between the central ion and the electric field leads to a phenomenon known as the splitting of energy levels. It's a bit like the dance taking an unexpected twist, changing the rhythm and pace of the performance. Now, this is no random dance move. The splitting of energy levels has a profound effect on the properties of the crystal, most notably its color. It's as if our dance performance suddenly gets bathed in a new light, casting a different hue on the stage. Why does this happen? Well, when the energy levels split, it alters the way the central metal ion absorbs and emits light. Each level corresponds to a different color, and the specific arrangement of these levels determines the overall color of the crystal. It's like the final bow of our dance performance, where the unique arrangement of dancers on stage creates a beautiful and memorable spectacle. But it's not just about the aesthetics. The splitting of energy levels also impacts the chemical and physical properties of the crystal, including its magnetism and conductivity. So the dance doesn't just look good, it also affects how the dancers move and interact with one another. It's a complex dance, but one that's critical to understanding the intricate beauty and functionality of crystals. And it's all thanks to the crystal field theory, which allows us to appreciate not just the visual spectacle, but also the underlying mechanisms that make it possible. So the beautiful colors in crystals are not just random, they are a result of complex interactions at the atomic level. Now that we've danced with the theory, let's see where it takes the lead in the real world. Crystal field theory, while seemingly complex and abstract, has numerous practical applications. For starters, let's consider the dazzling world of gemstones. Ever wondered why rubies are red and sapphires are blue, despite both being made of corundum? The answer lies in the dance of the ions we discussed earlier. The different metal ions in rubies and sapphires interact differently with the electric field, leading to a different splitting of energy levels and consequently a different color. It's like changing the main dancer in our performance and ending up with a completely different spectacle. Moving on from the beauty of gemstones, crystal field theory also plays a critical role in scientific research. For instance, in the field of materials science, understanding the behavior of ions in a crystal lattice can help in the design of new materials with specific properties. These could range from superconductors for efficient energy transmission to biocompatible materials for medical implants. It's as if our dance performance isn't just for show, but can also inspire new choreographies for practical purposes. Finally, let's talk about technology. Ever heard of data storage devices like hard drives? They operate on the principle of magnetism, a property directly influenced by the splitting of energy levels in certain metal ions. By manipulating these energy levels, we can control the magnetic properties of a material and hence its data storage capabilities. It's like using our dance performance to send specific messages, each move encoding a different piece of information. So, as we can see, crystal field theory is not just an elegant dance of ions in a crystal structure, but a tool that shapes our world, from the sparkling gemstones we admire to the advanced technologies we rely on. The next time you see a crystal or use a technological device, remember the unseen dance of ions that makes it all possible. From the colorful world of crystals, we move on to the captivating realm of mineralogical spectroscopy. Imagine the universe of minerals, a dazzling array of colors, shapes and structures, but there's so much more to these fascinating specimens than what meets the eye. Hidden within each mineral are clues about its composition and physical properties. And one of the most effective ways to unlock these secrets? Enter mineralogical spectroscopy. Mineralogical spectroscopy, in essence, is the study of how light interacts with minerals. When light, or more broadly electromagnetic radiation, encounters a mineral, it can be absorbed, reflected, or emitted. Each of these interactions leaves behind a unique spectroscopic fingerprint that can provide a wealth of information about the mineral's internal structure and composition. Think of it like a dialogue between light and minerals. The light asks, "What are you made of?" And the mineral responds by absorbing, reflecting, or emitting light in its own unique way. This conversation, captured and interpreted through spectroscopy, gives us insights into the mineral's identity and properties. But why is this important, particularly in the field of geology? Well, minerals are the building blocks of rocks, which in turn make up the Earth's crust. By understanding the properties of minerals, we can learn more about the processes that have shaped our planet over billions of years. From the formation of mountains and oceans to the occurrence of natural resources, mineralogical spectroscopy offers us a window into these geological phenomena. It's like being a detective piecing together clues to solve the mystery of the Earth's past. And the beauty of it is, every mineral has a different story to tell. From the common quartz in your backyard to the rarest gemstone in a museum, each has a unique tale encrypted in its spectroscopic fingerprint. Mineralogical spectroscopy, thus, is a key tool that helps us unravel the secrets hidden within the Earth's crust. It's a testament to the power of science, illuminating the hidden world of minerals and helping us understand the very fabric of our planet. So the next time you marvel at a mineral, remember there's a whole spectrum of information waiting to be discovered. Before we delve into the captivating realm of mineralogical spectroscopy, let's understand its basics. Spectroscopy, in its simplest form, is the study of the interaction between light and matter. You can think of light as a chatty explorer, venturing into the heart of a mineral and emerging with tales of its inner workings. Now, these tales are told in a language of light, a language that spectroscopy helps us interpret. When light encounters a mineral, it can be absorbed, reflected, or emitted. Each of these interactions happens at different wavelengths, creating a unique pattern or spectral signature. This signature is like a mineral's ID card, revealing its composition and physical properties. How does this work, you ask? Well, imagine the mineral as a complex maze. As light navigates this maze, it interacts with the mineral's atoms and molecules. These interactions are influenced by the mineral's composition and structure, leading to a unique spectral signature. It's like the mineral is whispering its secrets to the light. And spectroscopy, it's our way of eavesdropping on this whispering light, translating its tales into data we can understand. With these basics, we are now ready to delve deeper into mineralogical spectroscopy. So, buckle up as we embark on this exciting journey, exploring the hidden world of minerals and discovering the stories they have to tell. Let's delve deeper into the science behind mineralogical spectroscopy. This fascinating field of study is all about understanding the unique ways in which different minerals interact with light. To start with the basics, spectroscopy is a technique that studies the interaction between matter and electromagnetic radiation, which in simpler terms is light. Minerals, just like every other matter, have a unique way they absorb, reflect, or emit light, and these interactions occur at different wavelengths. Now, why is this important? Well, the pattern of light absorption, reflection, or emission can reveal a lot about the mineral's composition and properties. Picture it as the mineral's unique light fingerprint, if you will. Each mineral has a different fingerprint, and by studying these patterns, we can determine what elements it's made up of and even uncover its structural properties. There are different types of spectroscopy techniques that we can use to study these patterns. Let's touch on a few. First, we have infrared spectroscopy. This technique uses the infrared region of the electromagnetic spectrum, detecting vibrations within the mineral's molecules. It's like listening to the mineral's symphony of vibrations, each note revealing something about its composition. Next is Raman spectroscopy, which provides information about vibrational, rotational, and other low-frequency modes in a system. It's a powerful tool for identifying minerals and their crystalline forms. Lastly, we have X-ray spectroscopy. This technique uses X-rays to probe the electron configuration of minerals, giving us insights into their atomic and electronic structure. It's like getting an X-ray of the mineral's inner workings. So, each type of spectroscopy gives us a different piece of the puzzle, helping us build a comprehensive picture of the mineral in question. This wealth of information is integral to fields like geology, gemology, and even planetary science. So the next time you see a mineral, remember that there's a whole spectrum of information hidden within it, waiting to be discovered. Now that we understand the theory, let's see how it applies to the real world. Mineralogical spectroscopy, despite its complex name, is not just confined to the realm of high-end laboratories and research facilities. In fact, it has a significant presence in our everyday lives and contributes to various technological advancements. Firstly, mineralogical spectroscopy plays a vital role in the gem industry. Gemologists use spectroscopic techniques to determine the composition and authenticity of precious stones. For instance, the unique light fingerprint of a diamond can tell a gemologist whether it's a natural diamond or a synthetic one. Similarly, the vibrant colors of gemstones like rubies, sapphires, and emeralds can be analyzed to ascertain their quality and origin. Moving on to scientific research, mineralogical spectroscopy is a key tool in the study of our planet and beyond. Geologists use it to understand the composition of the Earth's crust, helping them predict seismic activity, locate precious metals, and even study the effects of climate change. Furthermore, it's not just limited to Earth. NASA uses spectroscopic techniques to study the composition of other planets and celestial bodies, contributing immensely to our understanding of the universe. Finally, mineralogical spectroscopy plays a significant role in technological advancements. For example, it's used in the development of new materials for electronics and energy storage. By studying the properties of minerals, scientists can design materials with specific characteristics, paving the way for more efficient batteries, solar panels, and electronic devices. As we can see, mineralogical spectroscopy is not just a concept, but a tool that shapes our world. From the jewelry we wear to the technology we use, and even the ground we walk on, its influence is undeniable. So next time you come across a sparkling gemstone or use your smartphone, remember the science that makes it all possible. We've journeyed through the captivating worlds of crystal field theory and mineralogical spectroscopy. We've unraveled the beauty of crystals, not just from an aesthetic standpoint, but through the lens of scientific theory. Crystal field theory, with its intricate explanation of electronic transitions, has given us a new perspective on why crystals display such a vibrant array of colors. We also delved into the realm of mineralogical spectroscopy, a tool that allows us to peek into the atomic structure of minerals. By analyzing the interaction between light and materials, we've learned how spectroscopy can reveal the composition and properties of minerals, thus broadening our understanding of the geological world. These explorations have brought us face to face with the intricate science behind the beauty of our planet's minerals. These theories, though complex, give us a deeper understanding of the Earth's minerals, bringing us closer to unraveling the mysteries of our planet. Thanks for watching us. Share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.